Hi guys, today we'll be solving a question in stability, particularly from the MV Hindship, and our focus today will be to calculate change of trim due to change of density. So if you have access to MV Hindship, this is actually a solved question, and I'll take you through the solved question first, and then I can discuss examples from the unsolved question. So if you have been watching my videos on ship stability, that's fantastic. If not, then the links to all the previous videos are in the description section below. There are about 53 odd videos before this, and I advise you watching those videos to have a good understanding of the basics of stability, ship stability, before you watch this video. So let's get started with this question, and I'll take you step by step on how to solve a question like this if you get it in the exam. So the question says that MV Hindship is at an even keel draft of 9.35 meters. That would mean that the ship forward and aft draft is the same, it's on even keel. The vessel is currently in dock water of a relative density 1.004. So the vessel is in port and the relative dock density or relative density is 1.004. What you have to calculate is the vessel's drafts or the change in the drafts forward and aft when the vessel reaches the sea. So when we say vessel reaches the sea, that means it departs the port and it goes out into the sea, where we assume that the relative density or the density of the sea water is 1.025. So the density changes from 1.004 to 1.025. That is the assumption you have to make to solve the question. You also have to assume that the fuel and freshwater consumption is negligible. So why they consider it negligible is because from the port into the sea it may not take too much time, so it can be assumed to be negligible because the consumption during that time may not be so significant to actually contribute to any change of drafts. That's the whole explanation behind it. Alright, so let's get started with the solution. You would need access to the Hindship tables or trim and stability particulars of the MV Hindship or motor vessel Hindship. So only if you have access to it, otherwise I'll show you where to get the values from. Alright, so the question says that the vessel's draft is 9.35 meters, but it is in dock water of relative density 1.004. So the first thing we have to do is from the hydrostatic particulars, which is given for seawater, we will find out the displacement for the hydrostatic draft of 9.35 meters. What would be the displacement? So if I go into the Hindship tables here, you can see that the hydrostatic particulars are provided here. So the hydrostatic particulars are here. This is provided for salt water. Specific gravity 1.025. So what you see written as SG stands for specific gravity. So it is specific gravity 1.025, and that is what it is given for. So what we'll do is we need to find the displacement for the draft of 9.35 meters. So let's see for 9.20 meters here on your extreme left hand column. The first column is the draft column. As you see on top, it's draft. The draft is in meters. So for 9.20, the displacement, which is the column next to it, is 19537, and for 9.4 it is 20024, but you need it for 9.35. so what you would do is you would take these values, go back into the calculation and write down these values here. So for 9.2, what was the displacement, and for 9.4 the displacement as well. Then what you do is you need it for 9.35. so how do you interpolate? So the difference between 9.2 and 9.4 is 0.20, and the difference between 20024 and 19537 is 487, as you see on the screen itself. So for a displacement difference of 487, the difference in the draft is 0.2, but you need it for a difference of draft of 0.15, because 9.35 minus 0.20, 9.20 is 0.15. So what you need is the change in displacement for a change in draft of 0.15. So what you would do is you would multiply this by this and divide it by this value here, because this is unknown. So the equation you get is 487 by 0.15 divided by 0.20, and you get the amount of 365.25. Now this is the correction value that you will apply. So this 365.25 means this is the change in displacement for a change in draft of 0.15 meters. Alright, so you would be adding this to this displacement, because you can see as you go from 9.2 to 9.35, the displacement must be increasing, because as you go from 9.2 to 9.4, the displacement is increasing. So displacement, and the triangle is actually a symbol for displacement. For 9.35 meters, you will be adding it to the displacement of 9.2, 19537 plus 365.25, and it will give you a displacement of 19902.25 tons. This displacement is for a seawater density of 1.025. This is not the dock water density of 1.004. Now the displacement for a draft of 9.35 in dock water density of 1.004 can be calculated by, if for 1.025 density the displacement is 19902.25, what would be the displacement for dock water density of 1.004? Take this here and divide it by here, and this is what you see in the equation above you. So when we multiply it, what we get is this displacement here. So the displacement for the dock water density is 19494.5 tons. Because the hydrostatic tables given to us is for the density of 1.025, we have to find out the values for the density of 1.025 and then convert it for a value of dock water density, or whatever is the relevant dock water density of 1.004 in this case. Now what we do is, for the seawater displacement of 19902.25 that you calculated above and draft of 9.35 meters, you have to find out the value of LCB, that is the longitudinal center of buoyancy. Alright, so we go into the tables again, same tables where we find out the values of displacement, and what we do is we go back here, and you can see for 9.35 you can find out the LCB values from here. This is the LCB value forward of the aft perpendicular. Alright, so forward of the aft perpendicular, it is the LCB value. This is also in meters. So you go back and find the LCB value. The interpolation is the same as I showed you before. This difference is for 72.223 minus 72.159. This is 9.4 minus 9.2. This is giving you the difference. So for a draft of difference of 0.2, the difference in LCB is 0.064. So what we need is for a change in the draft of 0.15, and that is what has happened. But in this case, when you find out the correction of 0.048, you can see the LCB value as you go from 9.2 to 9.4 is actually decreasing. So this time the correction you will apply, you will not add to it, you will subtract 0.048 to get the LCB for a draft of 9.35 meters. So what we are doing is basically finding out the LCB, because in this case when the vessel is on even keel, when the vessel's draft is the same forward and aft, the water is at the same level, what happens is the LCB coincides with the LCG. LCB and LCG are located at the same distance from the aft perpendicular, if this is forward and this is aft. Therefore, finding out the LCB on even keel helps us to also find the LCG, which is the longitudinal center of gravity. So when the vessel is on even keel, the longitudinal center of buoyancy equals the longitudinal center of gravity. Because we cannot find out the LCG values from the table, it is not given, we find out the LCB value, and then because it's on even keel, we just know that LCB will be equal to LCG. So here you have found out the LCG value as well of 72.175 meters. Now what we can do is we go back to the seawater displacement 19494.5 tons in seawater that we calculated, and we take that value and find out the displacement of 19494.5 tons in seawater. What will be the draft in seawater? Alright, so we've got the displacement. Remember, we calculated the displacement for seawater above. Then we calculated the displacement for dock water. So if you see from the beginning, we calculated firstly the displacement in seawater. To that we converted it to the displacement for dock water. That is 19494.5 tons. Now this is the displacement in dock water. 19494.5 tons is the displacement in the dock water. Now remember, when the vessel goes from dock water to sea water, there will be no change in displacement. Displacement doesn't change. It's only the drafts that change. Alright, so this is something you have to remember. You cannot say that displacement is the weight of the ship cannot change. The weight of the ship remains the same. It's only the underwater volume that changes, and because of the underwater volume, the drafts changes, because underwater volume is length by breadth by draft. Alright, so and since the vessel's length and breadth also remains the same, it's only the draft that changes with change in density. That's why the question is for change of draft due to change in density. So therefore, what we do is we take the displacement of 19494.5 tons, which is the original displacement in dock water of 1.004, but this will also be the displacement in sea water for 1.025. So we use this displacement as a reference point and find out the values of the draft in sea water and the values of MCTC, LCB and LCF. Now LCB stands for longitudinal center of buoyancy, MCTC stands for moment to change trim by 1 centimeter, and LCF stands for longitudinal center of flotation. Alright, so you know why we have taken 19494.5 tons, because that is the original displacement when the vessel was in dock water. That is the displacement. Displacement is not going to change when the vessel will come out of dock water and go into sea water. That is why we need this displacement to find out the rest of the parameters. So now we know we have the displacement 19494.5 tons. Let's see in the hydrostatic tables where this lies. So when we go back to the hydrostatic tables, and if I erase the rest of the values here, 19494.5, where does that lie? 19494.5 lies between 19051 and 19537. So that means it lies between the drafts of 9 and 9.2. So what you will be doing, you will be noting down these values of the two drafts, two displacements. You also need the MCTC, so you will note down these values as well. You will take down LCB, longitudinal center of buoyancy, as well as longitudinal center of flotation values. You will note down all these values from here. Also, I have to show you another value that you would be needing, and since we are on the tables, let me show you here. Forward part of the tables, you also have the length between perpendiculars values here, LBP, length between perpendiculars. You will take note down this value as well. So once you've noted down all the values, go back into the tables. I'll show you a couple of interpolation how to do it, and then you can do the rest. So let me show you how I found out the draft which will be the draft of the vessel in the sea water. The draft of the vessel in the sea water can be calculated because we have the displacement 19494.5, which lies between 19051 and 19537. So to calculate the draft, find out the difference between 19537 minus 19051, because this is the difference in displacement for a change in the draft by 0.2 meters, that is 9.2 minus 9. But we need it for the displacement of 19494.5. So for a change in the displacement of 443.5, which is the difference between 19494.5 minus 19051, we have to find out the change in the draft. Simple interpolation will give you a correction value of 0.183. This 0.183 we have to see whether it should be added or not. Now it has to be added because as you are going from 19051 towards 19537, the draft is increasing. So naturally, when you find out the correction here, you will add to the draft of 9 meters to find out the final draft of the hydrostatic draft at seawater. It will be 9.183. Alright, this is the hydrostatic draft, but we have to find out the drafts forward and aft. So this is the hydrostatic draft. We will go back and also find out the forward and aft drafts. But to do that, we need some parameters. So we have to find out MCTC. Now you can see here, I have found out MCTC. So MCTC can also be found out by the same way. But you have to remember, you have to take the displacement as a parameter. So for a difference of displacement of 486, you have a difference in the MCTC of 2.7. Where I got my 2.7 for? 214.5 minus 211.8. Alright, and this 486 is same as here. Difference between 19537 and 19051, which are the two displacements. But I need the change in the MCTC for a displacement of, or change in displacement of 443.5. Where I got this from? From here. So therefore, to find the change in the MCTC, I will cross multiply, find out the correction of MCTC 2.46, look at the MCTC values that going from 9 or going from 19051 to 19537, the MCTC is increasing. So going from 19051 to 19494.5, my MCTC should increase. So I will add it to the original value of 211.8, not to the original value, but to the value of the MCTC for 9 meters draft. As I go from 9 to 9.183, or I go from 19051 to 19494.5, I will be adding the MCTC and finding out the final value of the MCTC. So you can do a similar interpolation for LCB as well as LCF. Take the displacement as a reference point. Alright, and then find out the values. Once you find out the LCB and LCF, put it in the formula. Final trim T equals LCB minus LCG divided by MCTC multiplied by 100 times displacement. Now the displacement you know is 19494.5. The LCB you have just found out from above is 72.229. The LCG, remember you found that out as 72.175 earlier when LCB equaled LCG. On even keel, ship was on even keel, so LCB equal LCG, so the original LCG would be 72.175, and because you have not added any weights after that, the LCG does not need to change. Alright, so the LCG will not change because the gravity will not change without any addition or subtraction of weight. It's only the LCB that changes, because as you go from one density to the other, the draft changes, so of course the density will change. The draft changes, the density changes, so your longitudinal center of buoyancy also changes. Then you have found out your MCTC value above as well, and you know the 100 value is a constant. So put these in the values here. What you get is final trim equals 0.049 meters. Now the other formula you have to know is trim aft, which is TA. Trim aft equals final trim or total trim multiplied by LCF multiplied by LBP, which is length between perpendicular, the value that I showed you earlier. So you know the value of LCF, you found it out before. Put the values in the formula and find out the change in the aft trim. Then forward trim will be equal to total trim, which is T, minus aft trim. So 0.049, which was the total trim, minus aft trim change, is equal to forward trim, change in the forward trim. Now your draft in seawater was 9.183, which was the hydrostatic draft. Remember, we calculated here. This is the hydrostatic draft, 9.183. 9.35 was the draft in dock water. 9.183 is the hydrostatic draft in seawater. So as the density increased, the draft decreased. That is the relation between density and draft. So to the hydrostatic draft 9.183 forward and aft, you will apply the change in the trim that happened. Alright. So change in the trim that will happen, you will apply the forward correction here, TF and TA. Now how do you know whether you have to add the correction or subtract the correction? So what you have to do is you have to look at the values of LCB and LCG. Now the LCB value, as you can see, is 72.229, and the LCG value is 72.175. That means your LCB value is more than the LCG value, right? So that means when your ship is in the sea water, your LCB value, your center of buoyancy or LCB value is forward and center of gravity is aft, relatively. All right, let's say relatively. It's not much difference, but you can see, actually I am just showing you to exaggerate the difference. It's very close by, but still the LCG is aft of the LCB. The difference is not so much, it's very closely placed, 72.175 and 72.229, but G is aft of B. So when G is aft of B, that means the center of buoyancy is forward, so that means your forward draft will be lesser than the aft draft, because center of gravity acts downwards and the buoyancy acts upwards. So the forward draft, your vessel will be lifted by forward and sunk in the aft. That is why the forward correction you will apply, because the draft is reducing, you will subtract it and you will get the final forward draft. And because the center of gravity is aft of the center of buoyancy and the aft will be sunk, you will be adding the change in the trim aft to the hydrostatic draft and getting the final aft or final drafts aft. Alright, so I hope you have understood the explanation here for each of these steps that we have used, the formulas that we have used, and how to derive the values for the formulas. If there are any questions, feel free to write in the comment section. I'll try to answer it as soon as possible, or just let me know what you thought about this video and what changes you would like to see in the way I present it. Thanks guys, and I'll